I kind of already mentioned this briefly, is that the mineral aggregate, basically, you hear all these different terms: virgin mineral aggregate, rock, stone, gravel. They're kind of all referring to the same thing, basically, depending on the nomenclature in your area. But the aggregate has a big influence because, as I mentioned, it's a lot of times in wrap mixes as well. It's 90, 94, 95% of the total weight of the mix. So obviously the quality of that aggregate, the physical descriptions, all those things come into play. And from a volume standpoint, it's usually about 86 or 80% of the volume, and that has to do with the aggregate being about 2.5 times the density of the asphalt. So you see it: rock, granular material, mineral aggregate. Essentially, kind of the formal definition of aggregates in asphalt construction is any hard, inert mineral used in the production of hot mix asphalt. And South Dakota calls it asphalt concrete. North Dakota says hot mix asphalt. For an aggregate standpoint, and basically I'm out kicking my coverage here, but I've always enjoyed geology. The first 10 years I spent with the Wyoming DOT, well, started as a Wyoming Highway Department. I worked in the Central Materials Lab, which is not central, it's in Cheyenne, but we had to cover the entire state. One of the things that always kind of intrigued me in Wyoming, of course, you got kind of high desert plains, you've got river valleys, you got mountain ranges, you got the west side of the Continental Divide, the east side, and south central Wyoming. You got basically the red desert, which is when you're crossing I-80 in Wyoming, once you get west of Rollins, you cross a Continental Divide, east-west. But if you're east or westbound, you come off the east side of the Continental Divide, of course, everything draining to the Gulf of Mexico or Atlantic. But when you get onto the west side into the red desert, you're actually in neither. It's called the basin. Essentially, any water that falls into the next 20, 30 miles of road doesn't go anywhere, because then you cross the Continental Divide when you get to Bitter Creek Divide, kind of west of Wamsut or east of Rock Springs. Now you're on the west side of the divide. Everything in this, I don't know, it's probably 5,000-6,000 square miles is the Great Divide Basin. It doesn't go anywhere. Of course, it really doesn't matter because it gets about 4 inches of precipitation a year, and most of that's blowing snow. So it's on the move and blowing right through the Great Divide Basin, but it's kind of interesting. So the geology always intrigued me. So these different aggregate sources in Wyoming, all the way from hard rock sources to sand and gravel sources, had such a wide variation depending. Was it Green River Basin? Was it the North Platte River Basin? Was it coming out of the Laramie Range? Was it coming out of the Bighorns, out of the Snake River Range, and so on and so forth? And so basically, if you break it down, Mother Nature gave us the aggregate to work with, and how it gave it to us is kind of these 3 different ways: sedimentary, metamorphic, or igneous. And you can read the descriptions, but a lot of times what you find in sand and gravel pits is kind of a mixture of some of these, depending on the geology and the history of the area. So this is kind of an interesting map. I pulled it up a number of years ago in one of the state resource documents through the GIS Center. And this is the sand and gravel resources in North Dakota. I can't remember. I think this is like 1960 or something. And I just thought it was kind of interesting because you see these pockets. And, in western North Dakota, there's obviously a dearth of, quote, usable aggregate sources. And some of the aggregate sources that kind of were available in this area, if you can see my cursor, got thrown out anyway. Because what's the name of that material? It's kind of like asbestos, but it's a different family version of asbestos. I can't think of it right now.
Aeronite.
Aeronite, there you go. Thank you, whoever came up with that. My memory's I'm trying to remember more and more as I get older and older, and it ain't working. So what was I talking about again? Anyway, and of course the Minot area, of course, which is on the north side of the Continental Divide. The pockets in and around from Bismarck up to Washburn are kind of shown here. And then kind of these scattered glacial eskers that are kind of down in the Ellendale to Jamestown region. And then when you get into the Cheyenne, what's currently the Cheyenne River drainage, a lot of materials come from that area. You get down by Hankinson, from the big state and commercial owned pit, down by Hankinson. And then this Fordville area, which I mentioned earlier. And if you see the way that's lined up, that's kind of the old lake shore of Lake Aziz, the prehistoric lake of glacial meltwater. But what I found particularly interesting, besides where these deposits are, and you can see kind of how they were deposited by the color coding here, is these are the pre-glacial drainage patterns. So that's why you don't see the Missouri River kind of through here, right? This is pre-Missouri River. And so you had the Cannonball Heart River complex and tie the Knife River in from Dickinson area all east. That all flowed to the north. Then of course the Mouse River area here, and then the Little Missouri River and the Yellowstone River actually drained to the north. And then the Grand River, which comes out of South Dakota, basically west of Mobridge, and pretty much now drains part of northwestern South Dakota, came up all the way here and had a confluence with the ancient Red River drainage basin. And I think this is kind of intriguing because this is kind of where the original material deposited, and then it depends on how the glaciers impacted it from there on out. So this is that Lake Aziz that I was talking about, almost like a prehistoric lake of the woods, if you want to think about it that way. And you can kind of see down here on the edge of the Red River Valley, the current Red River Valley, is where the lakeshore ran, and that's that coteau, that hill, or bluff, if you want to call it, that runs in this Fordville area. Essentially, all those pits up in that area came from that portion. This probably isn't very clear. I think I can't even remember where I pulled this, I think from the North Dakota Geologic Society, but you can kind of put the aggregate into the current day. Now we have the Missouri River, obviously, that comes through here, and everything east of there is called the Coteau Slope, or the Coteau itself, which is kind of the water and wind deposited materials that were kind of shaved off. And this is that kind of blank area of little or no usable aggregate, or if it is there, it's spotted in these areas. Even at Williston, you get up into this Coteau area is kind of where you find most of the local aggregate sources for projects in the Williston area, if it isn't imported from Glendive on the Yellowstone River. So I just thought this was kind of interesting. And when you look at this, obviously when we get into the shale areas and doing our lightweight particle test, and how much shale do we have, and the +4, -4, and does it meet specifications, and can we process it out, is you kind of have this area along the Missouri Coteau that's kind of rich with shale. That's not just in North Dakota. I work South Dakota too, and it's the same way all the way down the river to Sioux City, basically. So I just kind of wanted to lay that out so you kind of have an idea. I include the South Dakota because this was a joint class, but I want to bring this up as well. Is obviously this is South Dakota, North Dakota borders here. And you kind of have three main features. Number one, glaciated versus non-glaciated environment is very clear in South Dakota, and it's East River, West River. This is the Missouri River. Everything east of the river is glaciated, and that's why you typically find your aggregate sources in these eskers or glacial deposits, basically, that were developed. Southwest South Dakota is very similar to southwest North Dakota. That's why there's a Badlands here and there's a Badlands in North Dakota. And anytime you kind of see these browns, that was probably a pretty descriptive color here because, they, instead of calling it aggregate, they could have called it crap, but the term was already taken. So from a transportation standpoint, these are really soft sandstones and so forth. But in South Dakota, you do have the quarry sources. This is the Black Hills. And these red formations, that's the Madison limestone, which is a fairly high quality limestone, which is quarried out in the Black Hills and Rapid City, Hot Springs, Spearfish, even the northern end of the hills. And then when you get to the eastern part, in this glaciated area, you have these quartzite outcroppings, which are denoted in red here. And quartzite is a very, very hard aggregate. Believe it or not, it's geologically, all that red material that's up in the Williston area, all that red dust, once it's compacted by Mother Nature over years and years and years with millions and millions of tons of pressure, becomes quartzite. And so these are outcroppings. If you've been down in the Sioux Falls area, the Sioux Falls is obviously named after the falls of the Big Sioux River. That's what's happening there. Quartzite is so close to the surface that the river, as it's flowing south to its confluence with the Missouri River at the very tip down here, had to cut through this quartzite and created these waterfalls. And then you get up in the northeastern part of the state, and of course, if you cross the line into Ortonville, Minnesota, and so forth, you have these granite type. So this is kind of anytime you're in tertiary materials, you're pretty much outside the zone of usable aggregate from a transportation standpoint. So this area here on the glacier side is defined by the James River, which obviously runs all the way from southeast of Minot down to the Missouri River, the confluence here east of Yankton, and the Big Sioux River, which runs kind of, it's the opposite of the Red River, runs to the south, obviously, but it defines the gravel deposits there. I actually pulled this from the Eros Data Center, which is north of Sioux Falls. I had a friend that worked there, and this is the upper level satellite imagery of South Dakota. And it's interesting. Obviously, you can see the Black Hills here, which was a very ancient uplift. Predates the Rocky Mountain, the Laramide orogeny tectonic plate upthrust. But you can really see these. This is the Jim River Basin, basically. And these are those coteaux, the Missouri pre-slope coteau itself as well that you saw in the North Dakota shot. So that kind of dictates, we can use what Mother Nature gives us. And if we understand kind of how Mother Nature put it together, it can kind of give us some insight to what the issues are and usability is of the aggregate. There are a lot of synthetic aggregates as well. You get in the Chicago area, Gary, Indiana area. There's a lot of slag from iron production. And interestingly enough, Ross Benson, who used to work with DAPA teaching these classes 20 years ago, and he worked with a consultant that worked with the Illinois Tollway Authority, still does. They used a lot of that iron ore material in their surface courses because obviously Chicago's in a mixed environment area, a lot of freeze thaw, get snow, ice, so forth. It's very high in friction. In fact, if you put it in your hand and rub it too much, if you didn't grow up on a dairy farm or do much manual labor, it's going to cut your hands up pretty good. And so this blast furnace slag is very common, getting kind of short as well, believe it or not, because they use so much of it for wearing courses in the Chicago, upper Indiana area. High skid resistance, the more texture and the more angular material it creates, this VMA, voids and mineral aggregate, which we'll talk about here, and it's using a waste product. But we're dealing with natural aggregates, basically sand or gravel. When asphalt first came along, it was you cut bank the material, throw it into a trap, separate it on your +4, -4, coarse aggregate, fine aggregate, figure out your blend, kind of similar to the way concrete is designed today. But again, the different sources that I talked about here. So we're generally dealing with sand and gravel pits, and we're dealing with processed aggregates. Processing meaning that we're crushing and screening and washing or air separating that material to produce the material properties and the gradation of the material we want. So this happens to be in a quarry. You can kind of see with the permanent setup of the belting and the screening. Why do we crush it? Well, first we want to reduce the size. The typical Superpave nominal maximum aggregate size mix in North Dakota is 12.5 millimeter ½ inch. So it's pretty hard to fit a 1-inch aggregate or a 3/4 inch doley or an 1.5 inch doley into that mix. So we have to crush it to reduce size. But it also helps improve our particle size distribution, our gradation, and we need that angularity. When we crush it too, it creates a higher friction surface on that crushed face. And then we're going to change it from maybe a rounder particle to an angular shape to give us that. So we got cone crushers. This is just kind of a breakaway of that. Why do we wash it or air separate it? Is, again, first and foremost, if there's any clay, to get rid of that clay. It can adhere to the rock surface, it can promote stripping of the asphalt from the aggregate, and it sucks up a lot of kind of expensive asphalt binder itself. So here's a typical wash plant, where we're going to air separate or water separate it. Works great. The problem is production's pretty low, and it's hard to do this in the winter, right? I wouldn't want to be running a wash plant this morning. So another kind of different type of wash plant. What we see more and more now in the last 20 years, it's increased greatly, are these air separators, where you cyclone separate the materials with air velocity, basically. Taking the finer materials into a cyclone and removing it and leaving the heavier or higher quality fine aggregate in your live stream. So the first thing really on an aggregate property we do is aggregate gradation. And again, that's just particle size distribution. There's dry and wet side. In aggregate testing class, that's the first test we start with is gradation. It's kind of the skeleton, the basic information we need. And this applies not only to hot mix asphalt, but to our aggregate base and a lot of other products as well. Just so you know, different states, we use percent passing in our specs in both North Dakota and South Dakota. There are some states that still use percent retain. So it's just tomato type of thing. We use these sieve nests, if you want to call them that. Basically, these are metric here with the English units in parentheses from largest to smallest. So on the left here is our coarse aggregate, typical kind of coarse aggregate sieve nest. And on the right here is kind of our fine aggregate. And again, largest to smallest with a pan underneath to collect everything that passes. In this case, the number 4 sieve. Once we know how much minus number 4 we have, what do? We run it through this nest or sieve nest to figure out what our fine aggregate gradation and then combine them. So some basic definitions in the base world. A lot of times they use the number 8 sieve as the separation between fine and coarse aggregate. But the couple things I wanted to mention here in the asphalt world is the number 30 sieve, which is 30 openings per lineal inch, and the number 200 sieve, that's 200 openings per lineal inch. And those two are important in the asphalt world. The percent that passes the number 30, kind of in the number 30 sieve area of the fine aggregate, I like to call it the sand fraction. And that can really help an asphalt mix. Number one, is typically more solid, more stable material. It's angular in a lot of our sand and gravel pits in North Dakota, and but you can get too much of it too, and then it can make the mix unstable or the aggregate blend unstable. But the 200 particularly is called mineral dust. And if you think of the material that would pass through a number 200 sieve, it's still an aggregate material. We call it mineral dust, but it almost flows like water, and it can have a relatively small amount can have big impacts on an asphalt mix. Once we have our aggregate gradation, you got percent passing on the vertical column here and the sieve size on the horizontal here, is what we typically plotted against, and in Superpave is this 0.45 power chart. So the percent passing is in base 10. 0.45 power chart means that our sieve sizes are logarithmically plotted based on the sieve size in metric to the 0.45 power. Why that comes into play and why we plot it to determine if our particle size or our gradation is going to work for us and what we need to do to adjust bin splits or materials is if we take this 0.45 power chart and we put a dot here at the origin, 0% passing, 0 size, and we put a dot up here at the maximum aggregate size. In this case, here's our 12.5 mix. That's our nominal maximum aggregate size. 19 millimeter 3/4 is the maximum size. And draw this straight line. That's called our maximum density line. And if our gradation, kind of illustrated by this dotted red line here, falls to the left or upper side, we call that fine graded. So on the number 8 sieve, for example, we have almost 78% passing. Falls on the right side or the lower side of that maximum density line, we call it coarse graded. That same number 8 sieve now only has 8% passing in this example. Why that's important is because the area represented, graphically represented under our gradation curve to that maximum density line is our VMA. And VMA is the voids in mineral aggregate. It's the intergranular void space in the compacted aggregate sample. So further it is, the greater the VMA. In the use in asphalt mixes, whether it was Superpave, Marshall, Veeam, any of the kind of standard mix design methods, VMA is extremely important. It's a common property, common volumetric property. Voids in mineral aggregate, the intergranular void space in our compacted aggregate sample. So the distribution kind of gives us that VMA. We need to maintain that VMA. That gives us the space to put our asphalt into the mix and to get adequate film thickness of that asphalt on the aggregate, but also sustain or maintain our air voids in that mix. That's the third A of those 3 A's we started with. So depending on the shape and the curvature of this line, we can have coarse graded mixes, we can have fine graded, we can have gap graded mixes like the SMA on 94 west of Jamestown or south of Hankinson to the state line on I-29. Important definition though, and Superpave established a common definition across the country for these maximum and nominal maximum aggregate size. The nominal maximum aggregate size of our mix is the first sieve one size larger than that sieve that retains more than 10%. So as we look at our gradation here on the left, for example, this sieve is the first sieve to retain more than 10%, in this case 28%. And therefore the blue here is the nominal maximum, and by definition the maximum is one sieve size larger. So in Superpave you have these different nominal maximum aggregate size mixes from basically here 1.5 inches down to 3/8 of an inch. The other unfortunate Superpave designation, when it first came out in the early 2000s, a lot of states meant, oh, then we got to have a lot of large stone mixes. And these are mostly quarry states. And boy, was that a misconception, because large stone mixes are very hard to compact and very hard to work with and can be very expensive. So here's just some cutouts of some gyratory plugs or pavements with the different nominal maximum aggregate sizes. And typically in North Dakota, this is what we're looking at, this 12.5, whereas you go over to 1.5 inches or 37.5, you can see large stone mix. More and more now, there's kind of a push. Grand Forks District has done some work on it. There's a push to do these thin lift overlay mixes so that we can keep the lift thickness down and still use conventional paving and compaction. And so I know Kurt Dunn in Grand Forks District has done some work with the Fordville conventionally produced aggregate materials to develop a 9.5 millimeter Superpave mix for North Dakota. So we talked about these properties. Again, the suitability depends on what our specification and end use is of those materials. Cleanliness in our area, particularly shale, is one of the big items for North Dakota. That's why we have a lightweight particle test required. Toughness, I talked about this with the LA abrasion test. The local materials, again, we do actually have some fairly good LA numbers in different parts of North Dakota and other areas. Like southwestern North Dakota, there's very little hard material. And this is that LA test apparatus that I talked about. You definitely want to put it in a different room with some soundproofing if you're in a permanent lab, because you're going to throw your plus 10 or plus 12 sieve coarse aggregate material in this drum. Depending on your specification, throw these steel ball bearings in there with it. Get a weight of the minus 10 or 12 sieve going in. After you bounce them around in this drum for several cycles, you're going to measure it and see how much that aggregate's broke down. As I mentioned, texture, the three big factors for VMA are gradation, or particle size distribution, shape of the aggregate, and texture. And that's what gives us the cohesive strength, the internal strength of the mix, and then we put our asphalt binder in with it. Rougher surfaces increase mixture strength because of the friction itself. Smoother surfaces, like this one here on the far left, produce a sliding or ball bearing effect. And the other kind of biggie in the asphalt world is these rougher textured surfaces, say here to here, the asphalt's going to adhere a lot better to this. Surface area may look the same, but if you look at it in 3 dimensions, there's a lot of ridges and valleys here, so the asphalt can bind and coat on this aggregate, whereas you may have difficulty getting it to coat and stay on that aggregate piece. So the shape is important, whether it's coarse aggregate or fine aggregate. One of the last steps of Superpave was to do what's called moisture sensitivity testing. And in some cases, asphalt and aggregate don't get along. And that's generally has to be addressed chemically. It's part of the rheology of the aggregate and the rheology of the asphalt. Of course, the asphalt comes out of crude oil. So a lot of times, for example, in South Dakota, they just use hydrated lime in all mixes as a mineral filler. Because when you get over into that quartzite area that I showed earlier on that geologic map, this quartzite doesn't always get along with asphalt. And so rather than using a liquid anistrip, South Dakota did a lot of major research and said, hey, we can put hydrated lime in all our mixes. It helps resist this stripping problem where the asphalt separates from the aggregate, but it also helps with some of the other properties of the mix. Absorption is a biggie in our part of the world in North Dakota. Is all aggregate, natural aggregate basically is porous. It will absorb water. If you've done concrete mixes, you know that as well. Absorb versus free water for running your water cement ratios. But if it absorbs water, it will also absorb asphalt. And we can run a lab test to determine the bulk specific gravity, apparent specific gravity, and the water absorption of aggregates. If we know the water absorption, basically we can thumbnail the asphalt absorption. If our water absorption is 2%, the asphalt absorption is probably going to be around 1%. Asphalt's a lot bigger molecule, so it won't penetrate into those water permeable pores as far as water will. So in the asphalt world, though, where it hits us is 2 ways. Production cost is the first one. I mentioned earlier when the stockpiled aggregate hits the drum, the first thing we got to do in the drum is get the water out, the moisture out. So higher absorption on the aggregate, the wetter the stockpile, the more burner fuel it takes to get the water out before we can even heat the aggregate up. So it's that drying time. On the asphalt side of it that's our expensive product. And by the time that material hits the paver, that asphalt absorption has to occur. If not, it's going to keep occurring on any hot day afterward. And basically will continue forever, but it's asymptotic. It levels off the rate at which it does so. So it can cause issues with construction, cost issues, production issues. As I already mentioned, Superpave came about in the late 1990s, early 2000s. North Dakota DOT was kind of an early adopter nationwide of Superpave. Superpave was just an acronym for superior performing asphalt pavement. In my mind, was a pretty bad acronym at the time. I know in 2000, 2001, I was the city engineer in Sioux Falls. We moved back from Wyoming, 20 years in Wyoming, and moved back and I was kind of recruited to be city engineer in Sioux Falls. And when I started talking to people, we had neighborhood overlay programs and CIP projects and so forth. And I said, well, are you using Superpave? And kind of the response was, well, we don't need Superpave. Most of these are subdivision streets. And I said, well, Superpave's got nothing to do with traffic classification as far as the system itself. In fact, it designs for local roads. It designs for the highest volume interstate corridors in the United States. I said it does so by changing the aggregate requirements or specification tolerances and specification limits, and then the mixture requirements. And so it was kind of a bad acronym, if you ask me, to start with, because a lot of counties and cities shied away from it because they said, well, we don't need Superpave. We don't need a Cadillac. We live in a Chevy world. And that was a total misconception of Superpave. And Superpave was a system, kind of a full circle system that talked about not only aggregate specifications and criteria based on traffic and environment, the asphalt selection based on traffic and environment, geographic location, but also particular aggregate specification requirements for these different traffic classifications. And then kind of closed the loop with a new kind of compaction system instead of the Marshall hammer, which we used for years and years and years, which essentially was a falling weight Marshall head onto a specimen in a 1,500 gram, 4-inch by 1.5-inch mold to both design the asphalt and to control the production of that asphalt during construction, to what was called the Superpave gyratory compactor, which is about a 4,700 gram sample that's 150 millimeters by 115, so roughly 6 inches by 4.5 inches. So a much bigger sample, and that's what we use to design our asphalt mixtures or job mix formulas, as well as control the process in the field. So on the aggregate side, not that most of these weren't around in the Marshall era. Coarse aggregate angularity here you can see is the first consensus property of a Superpave aggregate. And the two types of aggregate properties, whether they're physical or quantitative or qualitative, were separated into two different types: consensus properties and source properties. Consensus properties on the aggregate side were coarse aggregate angularity, fine aggregate angularity, flat and elongated particles, and clay content. And the source property, aggregate properties applied to a Superpave project were toughness, soundness, and deleterious materials. So all those probably look familiar if you've worked for a while or even in the Marshall world prior to Superpave in North Dakota. Well, coarse aggregate angularity is just fractured face. And of course, coarse aggregate stands for all the +4 material in our aggregate blend. +4 sieve, meaning a number 4 sieve is, if you look at the mesh in the sieve, is 4 openings per lineal inch. So plus number 4 material is considered coarse aggregate or rock, if you want to call it that. And it's all the plus 1/4 inch. In fact, it's slightly a little less than 1/4 inch subtracting the diameter of the wire in the sieve. So 4 openings per lineal inch minus the diameter of the wire in the sieve. So all that plus 4 material or coarse aggregate material, you run a fractured face count on it. And well, we had fractured face in the Marshall world for a long time. The fractured face test method in North Dakota, if you look at the number of it, is one of the lowest numbered in the series, which means it's been around since Moses was a baby, basically. So that's been around for a long time. The next one is kind of important. This is fine aggregate, so this is all the minus number 4 sieve material, the sand and fines, so to speak. And shorthand term is FAA, fine aggregate angularity. And in the Superpave world, FAA measures the angular nature of the material, the texture of the material. And in North Dakota, that becomes extremely important because we don't have a lot of the item above, the coarse aggregate, because we run out of all sand and gravel pits basically in North Dakota. There's no quarries in North Dakota. And so FAA became such a descriptive term and test for our aggregate sources in North Dakota that it's actually in the bid item now. When you look in the North Dakota DOT bid items, you'll see Superpave mix followed by an FAA number. It's being consolidated now, but originally it was Superpave FAA 45, Superpave FAA 44, Superpave FAA 43, all the way down to FAA 40. Well, that FAA that's in the bid item is actually the specification minimum for fine aggregate angularity. And that's how important it is. And what was quickly apparent in the conversion to Superpave, particularly in North Dakota, is strength doesn't necessarily come in big rock. Strength comes from really 3 items, regardless of the size of the material. It's the angularity of it, you know, how sharp the edges are. It's the texture of the surface, the friction, if you want to call it that, and the gradation, the particle size distribution that we're using. So there's a lot of history now, particularly once the Bakken formation hit, that Superpave mixes perform well in the highest traffic applications, probably in a 6 or 8 state area, when all the heavy truck traffic hit, you know, the western 18 counties, shortly followed by all the counties in North Dakota. And so FAA, or fine aggregate angularity, we'll talk about that a little bit more, but was a really important feature. What did we do before Superpave as far as trying to assess that material property, aggregate property? Was there were 2 ways basically. One, you restricted the amount of, quote, natural sands that you allowed into the aggregate blend. So lower traffic volume mixes, you would essentially have no limit on natural sand. As you got into the highest traffic aggregate blends or mixes, what you would say is something like maximum of 20% natural sands, essentially pit run fine aggregate, which is really not, that's more of a thematic or a general look at the aggregate. It says nothing about its physical properties. So that's what North Dakota did. South Dakota, prior to Superpave, I did an aggregate class and mixed testing class here last week here in Pierre down at the DOT lab, and what they did prior to this fine aggregate angularity requirement was they specified the minimum amount of what they called manufactured fines. And a manufactured fines was a man-made definition, was if there's 3 basically quarry types in South Dakota, which you'll see in a photo up here. But basically, if it was shot rock from a quarry that was run through a crusher, all the -4 was considered manufactured fines. If you were running a pit face and running that material through a crushing and screening operation, the only way that fine aggregate or -4 could be considered manufactured fines if the material, the pit run material, fed into the operation, was scalped on a 3/4 inch slotted screen. All the plus 3/4 then went to the crushing operation. The crushing operation, any -4 that came off that crushing and screening operation with the scalped material was considered manufactured fines. But that was the only way. If it was scalped on a 1/2 inch screen, nada, 0 manufactured fines. So it replaced kind of 2 of these arbitrary directions in the fine aggregate world, aggregate property world, and replaced it with an actual physical test, a measured test. The third consensus property was flat and elongated particles, and that was to avoid these kind of long, thin pieces of aggregate material that aren't stable. We handle aggregate a lot of times during the production of hot mix asphalt, from not only the pit, but the haul to the plant site, the stockpiling operation at the plant site, from the stockpiles to the plant through this big drum I mentioned, and then out to the road. And then the torture doesn't end there for aggregate, because once it's windrowed in front of the paver, it goes underneath the vibrating screed, and then of course is subject to the impact forces of steel wheel vibratory rollers and rubber tire rollers and so forth behind the paver. So the intent here was to put a maximum amount of flat and elongated particles allowed in that mix, because if they break early in the stockpiling process, they change your gradation, particle size distribution. And that'll change the volumetrics of the mix. Worst case scenario, if they make it all the way to the paver and all this steel wheel vibratory roller hits it during knockdown phase behind the paver, is it breaks in the mat. Now it's not only changed your gradation, but it's an uncoated aggregate face in that mat. So that was the third thing, and consensus property. And the fourth one was clay content, or sand equivalent as it's kind of termed. And in the pre-Superpave days, typically what you would do is run what are called the Atterberg limits: liquid limit, plastic limit, and then PI, plasticity index. And it's a measure of the amount of clay in your aggregate stream or aggregate blend. And clay is very detrimental, particularly in, for gravel roads. It's great. You need some PI, you need clay. That's your binder. But in the asphalt world, clay is bad because it absorbs a lot of asphalt, number one, and asphalt's an expensive component of these 3As. But on top of it, it's not very durable, and it inhibits coating, getting that asphalt film thickness when you mix it onto aggregate faces. So think of your coarse aggregate or your rock. When you're trying to mix that material together, if you got a lot of clay, clay is really fine, and microscopically, if you look at it, it almost looks like a saucer, a thin saucer. So it'll keep asphalt from coating on the aggregate, which very hard to see with the human eye. But when it gets out in the field and that coating doesn't bond real well, what happens over time, exposed to traffic, wet, dry cycles and so forth, is it'll actually strip. The asphalt will come off the aggregate. So those 4 consensus properties, basically, you can think of consensus as we can actually take material from any source and make these properties. If there's too much in flat and elongated, we can crush it. We can use slotted screens and crush it. If we have too much clay, we can wash it or air blow it. If we need more fine aggregate angularity, we crush it a little more. We need more fractured face or coarse aggregate, we can crush it more. Doesn't say it's the cheap way to do it or the most economical way to do it, but you can make these materials fit those 4 consensus properties. The last portion of Superpave aggregate properties were source properties. And like the other tests we've talked about here for aggregate, these were not new. Toughness. Well, toughness and soundness. Toughness we've been running for a long time. Most field labs at one time had the old Los Angeles abrasion drum in it. And basically you throw all your +10 or +12 coarse aggregate into there with a couple ball bearings, these big ball bearings, and turn it on, and it's rotating like your dryer at home. It's like throwing 8 pairs of tennis shoes in your dryer and watching them pound around, but in this case you put steel ball bearings to knock the aggregate down. So we've had that for a long time. Soundness and deleterious materials, there's an old test method in the North Dakota spec for lignite, and the term's escaping me now, but it was friable materials, which was an old ball peen hammer test, basically, where you take the suspect soft particles, like any of the oxides, magnesium oxide, iron oxide, shale particles, and you'd knock them with this ball peen hammer, and if they broke apart, it was considered a non-sound material. The other source property that we still measure to this day, and we did pre-Superpave, was lightweight particle test, which in North Dakota is extremely important because it's a test for shale. So anyway, those source properties you can't find. In other words, if you need a lower LAR number, lower loss LA, harder aggregate material, you can't go into a sand and gravel pit and make it harder. I guess if you're polymer coating it or something like that, you could, but with conventional processing, you can't make an aggregate harder. It either is or it isn't. And so when they do pit investigations, actually once you have your samples and you screen them out, that's one of the first things you run is an LA test on your +4, actually +10, and to determine what its LA number is. And the lower the number, the tougher the aggregate, the less the loss in this kind of test. And soundness, if you have a lot of mag oxide and some of those things, you can't really remove them from the pit stream. So again, this first one is the coarse aggregate angularity. Again, this is consensus property. It's measured on the +4. In this case, the metric equivalent of a number 4 sieve is the 4.75 millimeter sieve. In the metric system, the sieve size is actually the space between the opening space in your sieve mesh or material. And again, for DOT, what's a fracture? Well, you can have mechanical fractures, but Mother Nature gave us some fractures too. And we'll look at that in the geologic map of North Dakota. When glaciers covered most of eastern North Dakota, you had miles and miles of heavy compacted ice essentially shearing against the bedrock. And when the glaciers retreated, they left these eskers, these kind of pockets of gravel. And these pockets of gravel, depending on the bedrock material when they sheared, the ice pack was our crushing. So there's natural fractures in a lot of our sand and gravel pits in North Dakota. So what we look at is, does it have a clean and clear and well-defined edge? And does it cover enough of the aggregate, the aspect ratio? If it's just nipping an end off a piece of an aggregate stone, say 3/8 inch aggregate stone, that's not a fractured face. It's got to cover a larger cross-sectional area to get the impact of this fracture edge and texture that we get from fractured face. Again, in the Superpave system, as you went up closer to where the wheels hit the road, you had higher and higher fracture requirements. That fracture, that angularity gives us strength, internal or cohesive strength in that mix, in that aggregate blend. And the higher the traffic section, the more trucks basically, the more fracture you need. Flat and elongated, again, this was one of the consensus Superpave properties. It was actually based on an original ASTM test, as you can see listed there. Basically, you used the 5-to-1 ratio. Longest dimension of 5, the thinnest dimension had to be greater than 1. If it didn't, it failed this test. We ran this with QC/QA in North Dakota for a while, but basically I've never seen a failing flat and elongated test in North Dakota. And you see it very rarely in sand and gravel pits, because Mother Nature kind of abhors these flat and elongated shards, if you want to call them that, or arrowheads. as well. And even in South Dakota, where, as I mentioned, there's three kind of quarry sources, far west, far east, and northeast in South Dakota, you very rarely, in fact, the only time I've seen a test that failed was with quartzite in the Sioux Falls, Mitchell area. And that's a quarry or shot rock material, and the flat and elongated was actually created by the crushing operation. Using the impact crusher basically in secondary mode during crushing and screening. So again, the higher the traffic volume, the less of these, it's a maximum number for specification, the less of these you want in the mix. And here's just a simple graphic of the testing apparatus. It's by the way, North Dakota had a spec for this too, flat and or elongated particles prior to Superpave. But essentially, you have a pivot point. You can see where the pin is there, the 1 to 5 pivot point. There's usually 3 points here, 4 to 1, 3 to 1. And you put the long dimension of your subject stone in here, tighten down the retent pin, and turn it around. If it passes through this way, it's a failed flat and elongated piece. But now you really don't see it in production testing in North Dakota because it never happens. And so we kind of take the highest target value on our testing time, limited testing time and resources, and test other things. This test, though, is extremely important in North Dakota, fine aggregate angularity. It's measured on the minus number 8 sieve material, so that's metric equivalent is the 2.36 millimeter sieve. Minus 8 material, again, is 8 openings per lineal inch, so a little less than 1/8 of an inch diameter will pass through that sieve. So the minus meaning all the material that's passed through that sieve. And basically, we're calculating air voids in a loose sample. Method A is what's in the North Dakota test procedure for fine aggregate angularity. Again, I already mentioned this, but higher traffic volume pavements or corridors with higher truck traffic have a higher minimum FAA requirement. And of course, lower traffic volume, lower truck traffic volumes are that FAA 40 or 42 range. The high truck traffic are the FAA 44, 45 Superpave mixes. The apparatus is really simple. It's a quick, repeatable test. Essentially, you prepare a 190 gram specimen off your minus number 8 material, either from your cold belt feed or stockpiles and combined when you're looking at mix design. This little sample container here is placed. This is about 115 millimeters, the height of this, which is about the height of a gyratory plug as well. And then you have this little calibrated container down here. I like to call it the brass shot glass. And we calibrate that because now we can get a known volume in that cup. And of course, we have a tare weight of that cup. And essentially, you hold your calibrated AASHTO finger over the funnel here, put your material in here. Gravity does the work and drops it 115 millimeters into this cup. And takes very little time. And the idea behind here is the more angular that material is and the higher the friction is on the face of that fine aggregate, what's going to happen as it falls? It's going to kind of stabilize itself. The edges are going to lock together and it's going to leave more air voids in that sample. The rounder and smoother that minus 8 material is, as gravity does its work and drops it from 115 millimeter, packs it into that container. And as it's packing it in, what's coming out? Air. So it's lower air void content. So the process is fairly straightforward. It's, as I mentioned, it's real repeatable. And this has kind of become one of the main features after LA, Los Angeles abrasion test, of looking at sand and gravel pits in North Dakota. And are they suitable for Superpave or higher traffic volume asphalt mixtures? So the calculation we actually do there is we figure, once we've dropped this with a known volume, once we figure out the volume of the aggregate in the cup, the remainder is air. So the more air, in case 45 means 45% air is in that cup, is the more angular and highly textured it is. FAA of 40 means 60% air in that cup, 40% material. So clay content, or sometimes called sand equivalent, was that fourth consensus property. Again, it's a fine aggregate test, replaces liquid limit PI testing. It's a little longer test. It's fairly repeatable. It's a more, I guess, intuitive way of measuring clay content, or the opposite, sand, in my material. Then liquid limit PI is kind of a empirical test. Don't get me wrong, it's worked well for 80 or 90 years, but if you've ever run that before, it's really operator sensitive and testing sensitive, and sand equivalent or clay content was a way to use that. Basically, in the sand equivalent or clay content test, what we do is we introduce our sample into a stock solution. That stock solution is actually calcium chloride in solution. And what it does is the clay actually floats up in that contact solution because it's this thin saucer-shaped material. It kind of floats or suspends, I guess is a better term, in that stock solution. The sand deposits at the bottom of this graduated cylinder. And so after we've mixed it together, we've introduced the stock solution, agitated it in a mechanical shaker like this or a manual shaker. Once we let kind of the dust settle, pardon the pun, we can get a clay reading and a sediment sand reading right from the test. So the selection here on aggregate is actually really complicated when you think about it. Is a job is let out to bid and advertised, and say it's a Superpave FAA 45 project. Well, where's it at is the first thing. Is it in Grand Forks District? Is it in Williston District? Is it in Bismarck District? That plays a lot, obviously, because you have to look at this kind of delicate balancing act of how good are my local aggregates. Of course, the more local the aggregate, the cheaper it's typically going to be to haul. But if I have to do a whole lot of processing on it, and say for every ton of material I feed into the trap, I only get, 150 pounds of usable material to put in the stockpile, that's a lot of throughput. If you've ever watched Gold Rush on History Channel or wherever it's at, you'll notice one of the things they always talk about, what's the yield on this? Well, it's so many ounces per 1,000 tons of overburden, basically, or material that they're running. And it's a similar thing in the aggregate world here, is that you have to kind of analyze what can my local pits do, what can they get me, and I also have a timeline. It takes me a long time to process, since we have such a heavy loaded construction season between May and October and November. What happens in the spring? Most of our crushing and screening actually occurs during the winter. And the dry haul from that aggregate source to the plant site typically needs to be done before the spring load limits come on, because then the trucks can't haul at the capacity. And so if you're starting a project end of May, and that means, and it's an 80,000 ton asphalt mix, FAA 45, say, for example, that's what, 76,000 tons of aggregate plus any stock floor loss and plant loss. So you've got to haul roughly 80 or 90, haul and produce 90,000 tons of aggregate and get it in place for when the plant comes in May and gets set up and calibrated. So all that comes into play. And so there's a lot of this, this proximity to plant or job site, and what it's going to cost me either to haul or process my ton-mile haul if I got to dry haul the aggregate in? Does the site itself or the source itself meet the requirements? And if I'm opening up a new sand and gravel pit that, quote, I discovered, unquote, I need to test it for viability. Will it work? Does it have too much shale in it? Is the LA low enough, I should say? Is it hard enough? What's the FAA, fine aggregate angularity, depending if I'm going to do a two-phase crushing operation, say jaw and cone, or jaw and VSI, HSI, what can I make out of that aggregate source? And a lot of times the previous use of that source, I'll show you a little graphic here a little bit later. The Fordville area west of Grand Forks is an old ancient lakeshore from prehistoric lake, basically, of glacial meltwater. And that Fordville Ridge, or Coteau, there's been probably hundreds of millions of tons of material that's come out of that ridge. For Fargo, for Grand Forks, for the whole area, kind of between Devil's Lake and in the Red River Valley. And so this previous use of this aggregate is a good qualifier for, is it going to be good for this next project? And then, different competitors, crushing and screening is primarily a subcontracted operation in our world. You have the different, if it's Minot Sand and Gravel, Fisher Sand and Gravel, and so on and so forth. Some contractors have a crushing and screening arm as well. So that all comes into play. So Sharon, if you're still on there.
I am.
I've got 10 o'clock. Maybe it's time for just a short 5-minute break, and people can